morning and welcome to our Community Day. I'm Rick Bauer and I'm the Technical Director for Open Networking Foundation. And many of you already know Erica Johnson and her role as the Director of the InterOp Lab here at the University of New Hampshire. On behalf of both organizations, we're so glad that you're taking your time out of a busy day. Some of you are just moved out of dorms, and some of you are graduating. Someone is graduating, and then a week later is getting married, and all this stuff. And you came here to learn about SDN. That is so noble. Some of you need jobs in a few months, and will be coming back to us. And so that's noble as well. Your parents want you hired and making gads of money to support them. All right. We have an exciting day of events, and I'm going to ask Erica to walk us through what we're going to be watching. You'll be on video. All of these presentations will be...
Oh, we have an echo issue.
I love when my voice has echoes. It makes me sound regal. Or like a beagle. All right. All right. Go ahead. We're going to have a great day. All of these presentations will be up on our YouTube channel in the next week or so. But we want you to ask questions, make comments, help us in what we're doing, and we hope that you just learn a lot. And we'll have some more things to say about ONF later on. Erica?
Great, thank you. So welcome all to the InterOperability Lab. I'm Erica Johnson. First, a couple of housekeeping items. If there is an emergency, please exit to the nearest emergency exit. Those will be highlighted. You know, just save yourselves. Do not come back for your laptops or your personal items. And then we'll be having lunch. So everyone here is welcome to join us for lunch, and we're going to have lunch out in the front part of the building. And please help yourself to any coffee, water, and make yourselves at home. This is informal, so feel free to step out, use the restrooms, which is right out back if you would take a left or right out of the back door here. And yeah, and so we'll be hearing from many fine presenters. We have NoviFlow showing their Castor project demonstration. We also have someone from Princeton University. Thank you very much for coming. And then we'll also hear from Rick and a little bit more about the status of SDN and what ONF is up to. And then we'll see a demonstration from China Mobile. So this is very exciting. And then last but not least, we'll take a tour of the IOL if you're still interested. So again, welcome, and I'll hand it off to Marc here to be the moderator for the NoviFlow Castor project demonstration.
Okay, thank you. Yeah, and yeah, moderator is the key point here. So by the way, after the emergency that we're going to have, I'm going to be holding a used PC equipment sale out of the back of my car. If anything looks familiar, then
buy it.
Then buy it. So yes, I'm just moderating here. Essentially, this is the result of some activities that have been underway, the Castor project in Australia. So our gentle presenters for Castor project are Vijay Sivaraman from the University of New South Wales and Craig Russell of CSIRO. And they are actually doing this live from Sydney, Australia, where it is now, I believe, midnight or thereabouts. So we have to thank them for their dedication to the cause here. I'm now just going to get out of the way and pass the ball to Vijay. So Vijay and Craig, take it away.
Well, thank you very much, Marc, for the introduction, and indeed thank you for the opportunity to present our Castor project. As you say, it's a little bit past midnight here, but no worries. We had a beer each, so we're all good for the demo. So this project is about Castor, which is kind of an acronym we came up with. Stands for something like connectivity as a service to top of rack, or connectivity as a service rack. And it's meant to provide elastic software-defined interconnects of course, Craig's going to be giving us to the hard work of doing the demo. I'll be doing a little bit of talking, and I believe we also have one of the other team members, Himal, who's listening in, and John Matthews has been building some of the front end for us. So, so what we want to talk a little bit about today and show is a controller-based architecture that, in a software-defined manner, allows you to control your data center interconnects. And primarily the use cases we're targeting are twofold. Firstly, a public peering between autonomous systems at an exchange point, and I'm guessing you'll be seeing a lot more of that when we get to the SDX presentation next. But in addition, we're also looking at private peering between enterprises and clouds, because that is definitely a growth market, and one where we expect that many of the existing and upcoming interconnect points and data centers are looking to grow their business in. So in kind of a nutshell, why do all this? I think, if you look at the public exchange point use case, we can see some obvious advantages over a traditional layer 2 infrastructure. By the way, I'm hoping my audio is coming through fine. If there are any issues, Marc, please jump in and let me know.
You're loud and clear, Vijay.
Yeah,
okay.
Great,
If there are any, I can only see the audience as tiny dots on the screen. If there are any questions, feel free to interrupt and maybe relay the questions so that we can hear it and respond. So, if you look at a public exchange point, a traditional solution just uses a layer 2 switch. So the moment we use SDN, we get some benefits right away in terms of the enforcing basic hygiene of the switch fabric in terms of the kind of ether types that can flow, making sure that you only have one MAC address per port. There's no only unicast traffic, no multicast, no link local traffic, and so on and so forth. So those kind of benefits you can get pretty much straight off, which can be fairly significant in an exchange point, because typically today, if you look at an exchange point, they'll give you a set of rules when you connect in on things to do and not to do. But they really don't enforce it, because underneath is a layer 2 switch that will pass everything. So with SDN, the advantage is right away that you can enforce all that hygiene. And it's not just recommended or expected, but you actually enforce it. And one of the pain points in these exchange points are around ARPs, the fact that you can have ARP storms and flooding and taking up bandwidth from your switch fabric. We can pretty easily, using SDN, limit those to mitigate the impact of ARP storms. And looking forward, some of the more interesting things you can do are around better telemetry, better ability to actually see what kind of traffic is flowing across the fabric, who is it flowing from, who is it flowing to, and you can drill down to as deep as you want in terms of even wanting to look at a specific application traffic flowing between two domains. When it comes to the other use case around private peering, interconnecting enterprises to clouds, some of the advantages, of course, include the ability to scale up by adding data plane elements all under one logical control. So it's you can achieve much higher throughputs per rack, so to speak. You can also size the interconnects across peers to better suit traffic patterns. Cloud, after all, is based on the premise of elastic and scalable kind of payment models. We can have the network also provide that elasticity instead of being statically provisioned. So that's another advantage. And of course, you can also open up, since it's all APIs, driven by APIs, you can open up portals for customers to provision themselves, which definitely seems to be a trend that's happening in the industry. So in terms of physical layout, what we'll be showing today will contain a couple of NoviFlow switches, which act as the spine, as the leaf nodes in our kind of spine leaf. At the moment, we haven't quite put the spine switches in, but that's hopefully coming. And then we'll be just running some commodity servers, which will have your controller. We use the ONOS controller. It will contain your BGP speakers, which is just two Ubuntu machines with Quagga. We'll be running a Castor application, and we'll be running a web server. And that can act as your control plane and your management plane that can integrate with whatever other systems you have for telemetry, billing, and so on and so forth. So just diving a little bit into the demo setup. So by the way, whatever we're showing is actually running on our testbed, and Craig will also quickly show you what's on our testbed. We have 4 NoviFlow switches, and we have at the moment 6 or 8 sites that are already connected, up and live working, using our application, the Castor application, and in the next few weeks we'll be getting another few sites up for all of that, please. So the demo setup we're doing today is based in the lab. We have 2 NoviFlow switches, as you can see in the center. Above that you have the controller, which is ONOS, running our application, the Castor application. We have a couple of root servers, essentially for redundancy. So because we run ONOS with all the high availability, so there are 2 controllers and 2 root servers, in fact. And down below you can see the 4 domains or autonomous systems that will be connected through their peering routers into the Exchange fabric. So we have labeled them as carrier, enterprise, cloud, and cloud. So 2 clouds and a carrier and an enterprise. And we'll soon talk about, we use a mix of technologies here in terms of, a couple of these routers, peering routers are Cisco routers. One is a PK8 with Van der Becken software, and the other one's a NoviFlow. So we have a fairly heterogeneous kind of environment. In terms of how the demo is going to play out, the first step, we're going to start with a clean slate, right? Everything's been wiped off. This is going to show you step by step everything and the experience and how it is to set things up. Hopefully simple enough. Step 1 is just setting up, getting the, showing you the NoviFlow switches, spinning up the ONOS controller, the Castor app with the REST API, the Django backend, the MongoDB config. Again, the configs are not hard-coded into the application, as they are with some of the ONOS reference applications. It's all dynamically driven through REST APIs. It has a MongoDB which replays everything when you reboot it, and it has a React.js front end which lets you configure stuff. The front end is still a little bit crude. We haven't put as much time into making it nice and pretty, but given that it's highly modular and all driven with standard REST APIs, we are working on making a more beautiful version of it. Second step, we'll add the root servers, again, standard Quagga stuff. And third step is where it starts getting interesting, where you onboard a customer. We'll be provisioning the peering routers in each of the autonomous systems. As I said, it's a mix of Cisco and PK8 and Novi switches, one in each of the domains. And then we'll show you what the flow entries are and how the traffic forwarding is happening. The fact that there are only specific types, no multicast traffic, and going at 10 gigabits per second, though today you're showing at 1 gig or
no, up to 10.
Up to 10 today, fantastic. And lastly, we'll show you some of the more kind of interesting capabilities that we're starting to build into Castor, ability to see telemetry and graphs in real time, and the ability to go as granular as you would want. So with this, I'll hand it over to Craig.
Okie dokes. So I'm going to actually no. Go back to that. So we'll keep the diagram on that screen because we might have to refer back to that. So I realise there's a lot of parts in a demo like this, and I've been doing this stuff for quite a while, so I know what they all are. But if it's the first time you've seen it, it's easy to lose track of which pieces I'm dealing with each time. But we'll keep going. We'll see how we go. So as Vijay said, the first thing is essentially flows that just punt ARP packets to the controller and link discovery packets to the controller. Because I've not told the controller about the rest of the network yet, it's just sitting there waiting to be told what to do before it will install forwarding table rules into the switches. So that is what I'll do next. I have to remember all my steps. So I will run our web application and go to it. So this is another web page. Right. So this is the Castor front end, and as Vijay said, it's a little bit crude. It's our first cut at it, so it's not pretty, but it's functional. So if you remember the diagram, I'm now going to provision the two root servers by telling them what ports on the switches they are connected to. So the first one is switch number 2, port number 11. So I select that port there. I say it's a root server, and this is just a string, root server number 1. I also neglected to mention that the NoviFlow switch and the data plane is one IP subnet, 10.0.0.0/24, which is where I'm getting these addresses from. So I put in an IP address and I say commit. That's the first root server added, and you may not be able to see on the screen, but a little fiber went into the little socket there to make it look like it's it's connected. The second one is on switch number 4, port number 11. Same thing. This is the second root server. Root server number 2, 10.0.0.102. So I've now added the two root servers, and you heard Vijay mention that there's a Mongo database. This provisioning that I'm doing is storing that information in a database, so that if I turn the controller off and restart the controller, the database will replay that information. I don't have to enter it by hand. So the flows that go in have not changed because I haven't entered any peering routers yet, so it hasn't entered any flow table entries. So if I add a peering router now, and the one I will add is this one here, carrier-102. This is a Cisco router, and it's going in on switch number 2, port 12. So I will now provision that one. And then we'll start to see some flow table entries get pushed into the switch. So that's on port number 12. And this one is a peering router rather than a root server. And I'm going to call this one carrier-102. The 102 is just the AS number. 10.0.0.2. And so now if I switch back to here, so you remember this is polling a REST API to look at the flow table entries. There's now some more information in there. And if I filter it, import equals 12, sorry, slight error there. So look at this. This says, let's match packets coming in on port 12, Ethernet type hex 800, that's IP packets. There's two IP protocols there, 1 and 6. One is ICMPs, the IP version source, which is the peering router, and the IPv destinations, which are the root servers. That's so that you can ping them. And protocol 6 is TCP destination 179, which is the BGP port, and that's the output ports that those packets are sent to. If I now go to the root servers, lo and behold, there's now a BGP peering session with 10.0.0.2, and there's a network 202.9.2.80/28, which is that network there. So this router now, which has been trying to do a BGP session with these root servers, the controller has put flow table entries into the two switches to enable those sessions to come up. And so the BGP sessions have come up. There's no traffic can flow because there's nowhere for it to go, so I have to add another one. So what I'll do is go in and add another one, and then we'll start to see traffic that can go through the switch fabric. So I will now add, let's add, going between a lot of streams, I'll go to 413, and I will add carrier 103 -103 10.0.0.3. Okay. Oops, sorry about that. take just a minute or so to come up. Do you want to add the other views to it? Not just yet. Ah, keep making that error. So there we go. You can see. So we've now got a couple of prefixes in there. And if we go back to that input 12, we will now see we have this entry here, which is the data plane forwarding entry between those two peering routers. And I will now turn on my traffic generator. So on this diagram, I've got behind each peering router there is a network, and in that network I've got a traffic generator that's sending traffic from each autonomous system to each of the other three autonomous systems. So there'll be traffic going in every direction. If I turn that on, on the right screen, this is a Spirent traffic generator. I'll send that. Almost to that. So just looking down here, I've got, as I said before, I've got from each autonomous system 102, 103, 106 and 107, I've got traffic going, you know, cross to all the others, and I've added two peers. So these are the transmit rates down here, and I've now got some of the receivers working. So 102 to 103, transmitting 2.6 megabytes per second, receiving 2.6 megabits per second, and in the reverse direction as well. What I'll do now is I'll just add the other two. I don't need to talk my way through that because it's exactly the same process, so I'll just actually do it and the whole network will come up. So the other two peering routers, that's correct. So first one is 2-6, and then we'll have a look at some graphs. So peering router, this one is called Enterprise. And this one is actually an SDN router as well. It's a Pika 8 with a Van der Vechten controller. Some of you may have heard of Van der Vechten, which is a branch of RootFlow. That's correct. So add that one. Don't worry about that little error. There we go. That sometimes happens. And the last one is 4-7, if I don't make a mistake. Given that it's 12:30 a.m. Router, cloud, we're almost there. As I said before, you only have to do this once. This all gets stored in a database, and I could stop the controller and restart it and it would all be replayed. We will not do that now. There we go, that's better. So I will go back to and now our root servers now can see that last one's just not there yet. There we go. So the root servers now have functioning BGP sessions with all four peering routers. They're receiving prefixes from all four peering routers. And the root table, sorry, the data plane forwarding table entries in the switch, there's now a lot, but they're essentially like the sets we had before. And you'll see in this column here, packets, you start to see that all of these kind of entries here, which essentially are just import, Ethernet destination and an output, these are the ones where these packet counters are going up rather dramatically because I'm sending a fair amount of traffic here, and all of the traffic is now going. So here's the transmit values and the receive values. And let's go to the graphs. So this is Grafana. So this is another sort of web front end. So there's an application that also polls a REST API, an ONOS REST API, and essentially grabs these packet counts matching these forwarding table entries, sticks them in an InfluxDB database, and this just graphs them. So each of these graphs represents one of those peering routers or one of those autonomous systems. Carrier 102, Cloud 103, Enterprise 106, Cloud 107, and each one has three graphs, if you like, showing the number of bytes going from this particular autonomous system to each of the other three destinations. And the important point to note here is these are not just port counts, they're actually counts of bytes that match flow table entries, which is how you can break out what's going into a port. So we've got the Carrier 102 or the Enterprise 106 or whatever that peering router is physically connected to one switch port, but we've been able to break out the traffic to show the destination going to the different places. And those statistics will just grow over time, and you can zero in on them like this. You can have a lot of fun with Grafana. It's great. But that's essentially the point here, is that each curve is the amount of bytes going from this autonomous system to each of the other autonomous systems, even though they're all going in on the same physical port. So the last bit I'll do is I'll actually turn the 10 gig stuff on. So on the diagram, what I didn't show, that's a 10 gig link there, and that's a 10 gig link there. And I've also got a spine in here that will send 10 gig of traffic across there, and that'll make those graphs blow right out. So let's just do that for illustration purposes.
It's between the enterprise and the cloud.
Yep. So I'll just turn that one on. So if you look down here, these last two entries here, these ones are now sending just under 10 gigs, so 9.6 gig, receiving 9.6 gig. It's all going through the data plane. I'll just see the latency here is 30 odd milliseconds, microseconds rather. 30 milliseconds would be appalling latency, but 30 microseconds. So that's 10 gig going across that data plane between this autonomous system here and that autonomous system here. So it's going up with an NoviFlow switch across through there. And if I go back to this diagram and you'll now see this curve here, and look at the y-axis, we're into the gigabyte territory. This one here, this blue line, the Enterprise 106 to Cloud 107 and back, and that's why these ones have dropped down here, because of the scale. You can see the scale on this one is up in the tens of gigabytes, the scale on this one is in the tens of megabytes. Again, that shows you that that's a way of seeing that there would be a sudden spike of traffic between those two autonomous systems, and it's very, very quickly displayed when you do that. So look, that's probably about all we wanted to show. There is also in the front-end web app here, there is the ability to remove, so maybe I should just remove, want to remove one?
No, let's just summarize, I suppose.
I mean, you can play with this for a long time, there's a lot of other things you can do, but look, that in a nutshell, that's really what we've done. We've provisioned the system through a REST API using a web-based front end. That REST API goes to the ONOS controller and our Castor app on that ONOS controller, which exposes that API, and then the ONOS controller pushes the forwarding table entries into the data plane on the NoviFlow switch, which is what that is there. That's pretty much it. So Vijay's going to sum up on the, do you want to, final slide? There we go.
Right. So just to summarize, essentially, what Castor is trying to do is to develop or deliver an entire system for the interconnects. That includes, of course, the data plane, in this case consisting of the NoviFlow switches. It's using a carrier-grade SDN controller ONOS, which gives us the scalability, the performance, and the high availability that is required in the carrier environments. We have our application that's REST-driven, allows you to do live provisioning of the exchange. We have a Django web server framework and a MongoDB data store so that you can replay all the stuff each time you upgrade or reboot. And we have an HTML5 React.js front end that can provide the dashboard. As I said, the front end is still relatively crude. We haven't spent as much effort, but we are right now in the process of upgrading it, making it more flashy and easy to use. So at the moment, so far, what we've shown is maybe somewhat simple, just replicating the existing functionality in exchange points, but really treat it as a platform for innovation, because we've only started this project a few months back. We are currently operational on our testbed at more than 6 sites. I think eight sites spread across Australia. So
that's what this diagram here.
Yeah,
that was my lab system that we just provisioned. This on us here. This is the actual system that's running in Australia at the moment. That is a NoviFlow switch in Sydney. That one there is a NoviFlow switch in Melbourne. That one is a NoviFlow switch in Perth. That one is a NoviFlow switch in Seattle. And these are all the connected sites we have, which are universities around Australia, plus one of them is where we are sitting right now at CSIRO in Sydney. So there's, I don't know, 9 or 10 sites connected around Australia. And this system here is running the exact same application that we just showed. And this one here is Amlite, I believe. So anyway,
So this system is currently, functional, working on our testbed across Australia, and we are peering through Seattle onto Amlite and other research testbeds. We want to improve this platform further in terms of the telemetry, so that you can get the telemetry at multiple granularities. And this is where we are trying to engage with some potential use cases and trying to hear from customers what they want, and provide the bandwidth metering and the management capability. And we want to essentially allow the provisioning of the interconnect to the clouds to be elastic and potentially done by the customers themselves. So going forward, we are actually putting Castor into ONOS, into the next release of ONOS. Should be having Castor in it. So we're going currently through the code review and all that kind of processes. And our intention is to make this into a commercial offering. So I know that SDX is going to be coming up next, and Alpit's done some really great stuff. I think focusing more on the layer 3 aspects. Probably ours has been a little bit more on the platform side and building up the layer 2 at the moment. But we definitely want to work together and see how we can leverage each other's expertise in this. So thanks for that, and we're open to any questions that you may have.
By the way, the video on the laptop is open. We can see you. Okay, so you just raise your hand. Okay, so any questions?
Actually, we could probably
we could probably stop sharing the screen so that we can actually see you all the way. Yeah, that's a lot better. Yeah.
Oh, now the wheel rather than little dots.
So, do we have any questions?
Did people, did everybody vaguely follow what was going on? I know I zipped through that fairly quickly, and if you've not sort of seen that kind of stuff before, it can be a lot to take in. But I kind of, that's about as simple as I could make it.
Yeah, got a question in the back.
The damage graph that you're showing, how often were you following that?
I think somebody will have to relay the question because we can't quite hear it well enough.
In the graph that was showing the throughput between the different assays, how often are you polling that information?
Every minute. It's a Python application that just calls a REST API every minute, and that REST API just pulls the byte count from the flow table entry from the controller.
Do you have any other questions? Question?
So either that.
Did you hear the question? Are there any limits how high this could scale?
Are there any limits? I'm sure there are some limits.
Maybe are you talking in terms of number of peers or number of or data rates, or is there a more specific aspect to that question?
Number of peers. Number of peers.
Number of peers. Well, frankly,
No,
I mean,
want me to take
yeah, you take.
Yeah, so there's a couple of places where there will be scaling, right? For the number of peers, probably the thing that limits that is the software that's running on the root server, right? Now, for this demonstration, we've used Quagga. Quagga probably doesn't scale to a great number, maybe a few hundred. But Bird, the Bird daemon, which is used at most internet exchange points around the world, that scales to many, many hundreds of peers. And then that would also depend on the type of, bear in mind that this control plane just runs on an off-the-shelf server. In the particular demo there, it was just a virtual machine, as big as you provision the virtual machine, really. So it's just, it depends on the memory size. So, right. But we haven't really got to that stage at this moment in time. So.
Right, but definitely in terms of the data plane, we do not anticipate any problem. The number of flow table entries there is in the millions, if not more. So, yeah.
Other questions? Any other questions?
So, yeah, what do I say some this stage you have the how many controllers? How many controllers? Controllers in the demo? How many instances of Onos were you running in this demo? One?
Yeah, that's a very good question. In that demo, only one. The reason for that is we're on the mainline branch of Onos there, so it's 1.6, and the multi-controller part of that has got a bug in it and just doesn't quite work yet. The 1.5, which was the previous release, was fine, but our application uses some newer features that's in 1.6, so we're only running a single controller there. But as soon as that bug is fixed in the Onos release, you can run multiple controllers without any trouble.
Thanks, Greg. Any further questions? Okay. Well, yeah, one more.
We didn't hear that, so what was that, Mark?
The system that you have out there, are you peering with any major carriers, or is it only with, let's say, campuses or research groups?
So that the testbed network in Australia is it's all to university campuses and CSIRO. The core part of the network is run by ARNet, which is like Internet 2. You're probably familiar with Internet 2. It's Australia's academic and research network. It is a carrier network, but it's the carrier for the universities in Australia.
Yeah, but we don't really peer with any carriers per se. The peerings we have at the moment are with AmLite, which is again another research testbed. And we are looking to, we also had, for a while, we had a peering with ESNet, which is down at the moment. But again, we are peering with research networks, not with real, I suppose, not commercial carrier networks. And out of my own interest, can I ask if anybody in the audience is, I suppose, in the business of running exchange points or has any specific interest in this project? Well, if so, feel free to contact us.
They all want to create their own and make $1 billion. Well, we want to thank Craig and VJ. Thank you for your time, and have a beer on us before you go to bed. No one drinks Foster's over there, so whatever the best local beer is, have one on us. Thank you so much for your time, and on behalf of everybody here, we really appreciate it. Thank you.
Okay, thank you. Thank you for the opportunity. Thanks. Thanks again. Thanks, Marc. Thank you, everyone.
Good night, mates.
Bye. Good night. Good night.